Welcome. I'm going to solve impulse one step by step in case you'd like to see how to do it. So here's a little snippet from the reference tables. Here is a reminder that you need to somehow get from these formulas on the reference tables to whatever formulas here you want to use. Okay? All right. So great idea to fall back on your good habits of listing your data and listing your unknown, especially as we're working with new things, right? So force of 60 newtons, all right, is applied for a time of 0.8 seconds, and we are looking for impulse, and impulse is J, or as we made a joke, let's just call it Jim Pulse. Jim Pulse, there we go. All right, so we need a formula that has these things, and the formula is this guy right here. Okay, J equals FT, and that's just the beginning of this formula here. And keep in mind, this is a net force, right? So impulse and momentum are driven by net forces, right? Okay, so let me see, but we're not going to worry about, we're not going to have like complicated problems where we have several forces and you have to figure out the net force in the momentum unit. Okay, so we're just going to plug and chug. J equals FT. So that's equal to 60 newtons times 0.8 seconds. And if you do the math there, you get that the impulse is 4.8. And just carry the units through. So this is a Newton second. Okay? And keep in mind that impulse, the unit for impulse is a Newton second, and that just comes from carrying them through. Don't be that guy that puts a slash in there because you're uncomfortable that newtons and seconds are next to each other. And the momentum unit, again, you just carry through, so it's equal to a kilogram times a meter per second. Now, it turns out that a Newton second is equal to a kilogram meter per second. And the reason for that is a Newton is a kilogram meter per second squared. So you can work on that derivation if you like. What this means are these are equivalent units, which means you can use either one. But basically, the rule of thumb here is carry your units through. Cool. All right, so that's a basic impulse problem. Most problems are going to be using this daddy. All right, so let's list our data and list our unknown here. Okay, so here we go. The mass of the bullet is 0.1 kilograms, up to a speed of 300 meters per second. This is a final velocity. And since they didn't tell you what the initial velocity is, you're going to have to assume that VI is 0. All right, they would have had to tell you if it wasn't. Ooh, we are going to run out of ink in this pen before I'm done with this thing. All right, and then the time is 0.001 seconds. Now, the formula is going to be useful here, and we're looking for force. That's our unknown. All right, the formula is going to be useful that has all these things is this, and keep in mind, it's not in your reference tables, right? So Ft equals m delta V. Now, you have to be careful with the delta if there's more than one speed, because technically delta V means final minus initial, right? But in this case, the delta V is going to be 300 meters per second minus the initial, which is 0. So the delta V is 300 meters per second. And actually, that is, yeah. Yep. Cool. All right, so let's plug in here. F times 0.001 seconds equals the mass, which was 0.1 kilograms. That's one heck of a bullet. That's like 0.2 pounds. And the delta V was 300. Okay. So if I do my math there, I get that the force is 30,000 newtons. Okay. Now, that may seem really big, but again, we're talking about a 0.2 pound bullet. Okay. That's pretty incredible. Okay. Now, what we have here is, so let's just list the data here and I'll draw a picture in a second. So we have the mass of the Starship Enterprise is 3.79 times 10 to the 9 kilograms. Okay. It's going from rest to a final speed of light speed. Okay. And the time is 120 seconds. Okay. How much force are we going to need to get there? Okay. So here we go. Again, Ft equals m delta v is the formula we're going to use here. Okay. And the delta V, again, is going to be 3 times 10 to the 8 meters per second, because if you expand this out, you'll find that the change in velocity is that. All right, so force times 120 seconds equals the mass, 3.79 times 10 to the 9 kilograms, times the change in velocity, which is 3 times 10 to the 8 meters per second. And let's see what this is. So I'm going to pause while I do the calculation here. Actually, I might, just want to remind you that you can use that sweet E button on your calculator, remember? So if I'm putting this into my calculator, I'm going to literally type in 3.79, that EE button, 9. That's how I'm going to put that number in. Okay, pause while I do some. Okay, so I got the answer was 9.48 times 10 to the 15 newtons. Yes, this is a giant force. If they don't have those inertial dampers, everyone on the Enterprise is going to die. All right. We don't have real inertial dampers yet. Okay. Let's see. Let's list our data again. Mass equals 1,000 kilograms. We are supplying a force of 30 newtons. And we are trying to get the car up to a final velocity of 24 meters per second, because they use this reaches. And the initial velocity is 10 meters per second. And these are both going in the same direction. Cool. Now, this is a point where you have to be careful about that final minus initial, right? So delta V is equal to final minus initial, right? So the delta V here is going to be 24 meters per second minus 10 meters per second. So the delta V is 14 meters per second. This is different from in the egg example, where you actually have the thing going in the opposite direction, and we have a problem with that in a minute. All right, we're going to again use Ft equals m delta V. And now what we're trying to do is find time. All right. Boop. All right, let's see here. So 30 newtons times the time equals the mass, which was 1,000 kilograms, and the change in velocity was 14 meters per second. Okay, so let's just quick do that calculation. And we get that the time is 466.7 seconds. Cool. All right, let's do the next page. Okay. A circus clown. So now we have a recoil kind of problems. Or not really, actually, this isn't a recoil. This is a clown flying through a brick wall. Okay, so the mass of the clown is 100 kilograms. The force is 5,000 newtons. The time he takes to pass through the wall and apply the force is 0.5 seconds. And we're looking for delta V. So the formula is Ft equals m delta V. So if I just plug in here, 100 kilograms times 0.5 seconds equals the mass, which is 100 kilograms, and the delta V is what we're looking for. All right, so if we do this, I don't know why I need to do a calculator to do that. That's pretty funny. I did not look carefully. All right, there we go. Cool. And then finally, this is more like the sample problem we did in the mini lab. Okay, so mass of the tennis ball is 0.58 kilograms. It is served with an initial velocity of 50 meters per second. it is returned with a final velocity of 30 meters per second. And so since it's going in the opposite direction, I'm going to make it negative. Okay? All right. And what do we need to know? Cool. All right. So the change in momentum. So looking back at the problem solving thing. Okay. All right. All we're doing is finding momentum, the change in momentum, right? So we're trying to find delta P, right? And I can expand delta P to m delta V. And again, the reason the delta is in front of the velocity, not the mass, is because in these kinds of problems, we're not talking about the mass. The mass of the tennis ball is not changing, just the velocity. All right. So, fun fact though, if tennis ball goes super fast, it starts to get more massive, and that's because of relativity. Doop. All right. So let's just put in this. So it's m times vf minus vi equals, that's what we're looking for, the change in momentum. I guess I can make this an equation and just call it delta p. All right, so 0.58 kilograms times the final velocity, which is negative 30 meters per second, minus the initial, which is 50 meters per second, equals the change in momentum. All right, so when I do this, I get 0.58, I'm dropping units here, times negative 80 meters per second. And keep in mind, what's happening here is the ball is going from 50 down to 0, back up to 30 in the opposite direction. That is not a change in momentum or change in velocity of 20. That is a change in velocity of 80. Okay, if I then take that and do the math here, I get that the change in momentum equals negative 46.6. And we can just carry those units through. Kilogram meters per second. All right. Now, what is the impulse on the ball? Excuse me. Well, the impulse equals the change in momentum. Okay. That's the two outer parts of this equation here. So J equals delta P. Therefore, the impulse is also negative 46.6 kilogram meters per second. Or you could say J equals negative 46.6 Newton seconds. All right. Either of those are fine. All right. Hope that helped.